Okay, well, welcome everybody to our latest Northwest Quantum Nexus seminar series. We're very pleased to have Margaret Martinosi and Prakash Murali speak today. We are starting the seminar now, but we have a few things we wanted to relay before we got into the science part of the talk. So first, this seminar is being recorded, and by attending this meeting, you may appear as an attendee in the recording, and your questions, comments in the Q&A session and section of the chat will also be part of the recording. The Northwest Quantum Nexus, or NQN, has a code of conduct. We are dedicated to providing a respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that is harassing, and the screen just glitched. There we go. Okay. Or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards. We encourage everyone to assist in creating a welcoming and safe environment, and we reserve the right to refuse admittance to or remove any person from the event at any time at our discretion. Before I turn it over to Martin for the introduction, I'd just like to encourage everyone to visit the nwquantum.com website. We've set up a new mailing list there. Not only can you find the upcoming talks listed on that website, but you can also sign up for the MailChimp mailing list and get email reminders of the talks. Thank you. Martin, over to you.
Hello, thank you, Nathan, and hello, everyone. My name is Martin Rotteler. I'm a researcher at Microsoft Quantum, and it's a distinct pleasure to introduce our speakers today, Margaret Martinosi and Prakash Murali, both from Princeton. Margaret is a professor of computer science. She's extremely well known for her work on the computer architecture side, both classical and quantum, and many other areas as well, including mobile computing. She had many really seminal contributions to the quantum world. Also, we're going to hear today about some of those. I would like to highlight that she is also heading the size department, the size directorate of the NSF these days. And for those who don't know, that's kind of one of the biggest departments, definitely the biggest computer science department in the NSF, responsible for securing the future in computer science information technologies for the United States. That's a very important role. We're thrilled to have her, that she has time to speak to us today. I personally had the pleasure to organize a workshop with her a couple of years ago for the Computing Community Consortium on bridging the gap between quantum computer algorithms and what we can do with near-term hardware. And that's very much in the spirit of the presentation today. And that kind of brings me also to our second speaker today, Prakash Murali, who's working on exactly these topics in his PhD. He's a final year PhD student at Princeton, has had several terrific publications already. Some of his work was so influential that it was selected for the micro topics. For those who don't know, that those are like the top 10, 12 papers every year at all the major computer architecture conferences, ISCA, Micro, and so on, that gets selected. So it's a distinct honor to be in that group. So today, they're going to talk to us about closing the gap between quantum algorithms and hardware using compilation and architecture. I want to hand it over to Margaret next. Margaret, you have the floor. Thanks for being here today.
Thanks so much, Martin and Nathan and Mark and everyone else. It's great to get the chance to speak. When I was invited to give this talk, I was excited. This is a topic near and dear to my heart. But on the other hand, as Martin mentioned, I'm kind of two jobs, one person right now. And so partly for that reason, and partly because, as many people know, it's the students who really drive a lot of the underlying research. I decided that the best approach would be to tag team this. And so what you're going to see today is a tag team between myself and my very senior PhD student, Prakash Murali, who is, just moments away from graduating and who's been already a deeply influential researcher. Next slide, please. So quantum computing, as I assume many of the people on this call know, has extraordinary prospects. It has entranced us for years already because of the potential for exponential improvements in computation time, potentially making intractable problems tractable with relatively, so linear increase in qubit count can lead to exponential state space growth and therefore exponential improvements in expressive power. That's the promise. And some aspects of that promise were sort of articulated by Shor and others through things like the Shor's factoring algorithm. The reality right now is also fairly exciting. Hardware exists. Cloud connecting hardware exists. You can run on multiple platforms from essentially anywhere. Furthermore, over the past couple of years, we've also seen the first quote-unquote quantum supremacy demonstrations. That is, cases where at the time the experiment was run, there seems to have been an advantage of quantum over classical for solving the same problem. Now, there's often a cat and mouse thing where the minute someone shows a quantum advantage, someone else figures out a way to do it better classically. Nonetheless, we're starting to see these demonstrations at modest scale and across multiple platforms. Next slide, please. So one of the things that remains to be solved is that while there's great excitement at the algorithms level, this decades-long promise of things like Shor's algorithm, and there's great excitement in terms of the underlying hardware starting to sort of get up on its legs and walk for us, there's still what we call an applications to devices resource gap. And there's different ways to express this gap, but what we show here are years on the x-axis from 2000 to 2025, and qubit count going up the y-axis, and then a third dimension is shown in color, and that's sort of the degree of noisiness or error rate to the qubits that are being generated. And so what you can see is that over recent years, the number of qubits that has been built into a system has increased, and the quality of those qubits has improved as well. And you see this across multiple vendors. The era that we are currently in has been coined the noisy intermediate scale quantum, or NISQ era, and it refers to the idea that yes, we can build quantum computing devices, but they're still currently fairly noisy. They have error rates, as you can see, that sort of range 10% to 0.1% rather than being more perfect the way our classical transistors are. And intermediate scale, meaning this dozens of qubits kind of mode. Next slide, please. So that's the devices side. The applications side is that actually the number of qubits, the number of high quality qubits that would be required to do the kinds of applications that have captivated us, things like Shor's factoring algorithm, are orders of magnitude above what we can actually build. And so in shifting from the last slide to this slide, please note that the y-axis changed, right, from being sort of 0 to 50 to now 0 to 1 million. And so we have orders of magnitude gap between what something like Shor's needs and what current systems can provide. Fortunately, some algorithmic improvements offer some hope, namely things like VQE, variational quantum eigensolvers, and combinatorial optimizations like QAOA represent a new breed of algorithms that mix hybrids of quantum and classical together, iterate between them, and while they don't offer the exponential speedups of Shor's, they do offer the promise to make use of these systems sooner and with lower resource requirements. But even so, there's still a gap here. And so we have to think more about how to sort of address that gap. We need both sort of the ability to make use of relatively modest numbers of qubits and also the ability to make the best out of fairly low fidelity execution prospects right now. Next slide. So the real question, the question that my group has been answering is, how can we leverage the techniques, the best practices from decades of classical computer architecture and compiler research, bring them in and help them bridge the resource gap between quantum algorithms and devices to basically close that gap sooner and to offer an orthogonal way of accelerating progress beyond simply better algorithms and better devices. We can sort of create better mapping approaches that should bring the two together and bridge the gap more quickly. And I can tell the story now that the reason why I got into quantum is because of a fairly long conversation at a coffee pot with a physics colleague about a dozen years ago, where he was proposing a new kind of qubit. And he proposed it to me in terms that made me think, we have architecture techniques that could make that type of qubit more effective. Fast forward 12 years, and I think what my group and others in this space have found very rewarding and impactful is the chance to pull those ideas from classical computer architecture and bring them over and apply them. So if we're going to talk about that, we can go way back to the beginning. If you think about 1950 in classical computing, where were we in 1950 in classical computing? We had devices down low, vacuum tubes and relay circuits from which we were building large computers. You can see a picture of one here. We had invented a transistor in 1950, but we weren't yet using it in any computerized devices. They were being used for radios. And so one analogy to quantum is that 1950 in classical computing was very much early days and in many ways too soon to pick a winning technology. If you were going to pick a winner in 1950, you might have been tempted to pick vacuum tubes or relay circuits, and you clearly would have been wrong. And so it's interesting to think about the lessons learned from that we can bring into quantum, about developing techniques and stacks that will apply across a range of possible technologies. Another part of this analogy is that in 1950s classical computing, there were math and computer science people who were thinking well beyond the capabilities of the machines they had access to. Turing was already thinking about his quote unquote Turing test and artificial intelligence way back then, even though modern computers at the time were nowhere near being capable enough to execute anything like that. So already in 1950, we had a notion of an algorithms to resource gap. The other thing that is noteworthy about the 1950s is that there was a big gap, not just in terms of resource quantities, but in terms of the system layers to get the job done. And that is a third aspect that is aligned with today. We don't quite know the best way of connecting quantum algorithms to quantum bits. If you look at where we have sort of landed when it comes to today's classical computing, we have this kind of a stack that might be familiar to the computer scientists in the audience, where transistors have become the device of choice. VLSI circuits build from transistors, architecture, compilers, high-level languages, and so forth. When it comes to quantum, there's a couple things to note. First of all, the to-do list that we have is enumerated, but it's unclear where will be the best ways to do them. And second of all, the resource situation is so constrained that the idea of clear abstraction layers that block software's view of hardware are decades away. Where we are now is that we need to have full information flowing up and down so that we can do the best options for optimization that are possible to make the best use of hardware that's possible. And so sort of classic challenge is, how can we do that kind of full information flow and optimization in a way that takes advantage of knowing things about the hardware or the software, but without being so non-portable that it's tied to a particular technology? And so what a lot of the work in my group has done, what a lot of Prakash's work has done that you'll see, is figure out ways to draw insights from the hardware attributes or the software attributes, but not tie yourself specifically to one implementation. Next slide. And so here we are. Here's one example of sort of starting to build up that stack. One question that you could ask is about, for a given quantum implementation, what are the right gates to expose to software? And so, for example, IBM makes one choice about what are the actual gates that it implements versus what are the gates that it exposes to software. There is an analogous problem on the classical computer side of the house, which is to say, what is the instruction set architecture of a machine? What is the gate set? You can also think about this in terms of fidelity. does it help us if we can expose gates and their fidelity information, not just the operation itself? Next slide. And so the game here is to try to build compilers that can be aware of different gate options and be aware of different fidelity aspects, and then see which aspects of that awareness bias the most. Next slide. So we aren't the only group that's worked on this. A lot of people have worked on different aspects of QC compilation and architecture. Martin and I were both involved in some early IARPA work that funded aspects of this quite a while ago. But I think what we're seeing a coalescing towards are approaches that try to allow some amount of information flow, but in a parameterized way that allows for different types of portability across implementations. We're also sort of increasingly aware of the value we get when we account for things like noise and fidelity as part of the compilation, in addition to things like what gates are exposed. So there's issues where software not knowing about hardware takes away literally orders of magnitude of possible execution advances. Next slide, please. So what we're trying to do is avoid too much abstraction too soon and draw from classical instruction sets. Next slide, please. And in particular, what Prakash is going to show is that we can bridge both from the top and the bottom to create these kinds of cross-cutting execution stacks. In this noise adaptive compilation, you can see that as sort of taking ideas from the compiler community, including parameterized hardware information to create portable optimization approaches for it. So that's bridging that resource gap from the top. Next question, next slide. The other option is to bridge the gap from the bottom. And so, for example, we've done work to analyze different aspects of how design choices that hardware folks make can shape the application behavior and the compiler choices. A good example of this is something like the connectivity between different qubits that's available in trapped ion or superconducting implementations, and how that connectivity sort of shows itself in the ability to compile with short circuit depths that allow for lower error rates. Next slide, please. So in essence, this is about the sort of careful and principled co-design across that full stack, where we make good use of the information that would be available in full stack flow, but in ways that are hopefully parameterized, so that we're not simply developing compilers for a particular implementation. And you know, one of the advantages of doing this as a tag team is that I can say things about Prakash's work that maybe he would be a little bit shy to say himself. And so he will give some of this, but I will say that I'm really proud of the degree to which this work has had immediate and real impact. For example, being pulled into different commercial compiler stacks, real world impact on 5 different industry compilers and on a range of implementations and hardware software interfaces. So I think it's a neat example of sort of pulling ideas from computer science into this new arena. It's also a neat example of the possibilities for impact in an iterative way between the academic part of the research community and the implementation and industry part of the research community. Next slide. So with that, I'm going to hand the baton over to Prakash to present this work in a little more detail himself, and we will both be here to field questions at the end of the talk. Thank you.
Thanks. In this part of the talk, I'll first talk about my work on noise adaptive compilation, and then briefly talk about some of our upcoming and recent work on looking at instruction set design for these systems, and then discuss some avenues for future work and conclude. So Margaret mentioned that near-term quantum devices are quite noisy. So what this means in practice is that when we run an application on a system, we get a distribution of outputs instead of just a single output. So as a concrete example of this, here we show the executions for the Bernstein-Vazirani benchmark, which is a popular benchmark used to measure system performance. And we execute this benchmark 8,000 times on a fixed set of 4 qubits in one of IBM's 16-qubit devices. And in this case, the correct answer that we expect the system to produce is the string of 4 ones. But you can see from this distribution that that correct answer occurs in only about 35% of the runs. And this, we call this number the success rate. And essentially, it's important to have a high success rate if you want to be able to distinguish your correct answers from noise. And to show how important it is to optimize for success rates in the software layer, here we contrast the executions of another 4-qubit benchmark, where the correct answer is a string 1001, compiled first using IBM's Qiskit compiler from the time that we did this work, and our compiler, which uses noise awareness. So you can see on the left that when we look at the distribution from Qiskit, the correct answer occurs in less than 10% of the cases, and a wrong answer actually dominates the output distribution. While if you used noise properties and hardware awareness in the compiler, we can get the correct answer to dominate with in a significant fraction of the runs. So from the application side, the requirement really is that we want executions which have high success rates to be able to get correct and useful executions from these devices. And there are two main challenges for this from the hardware side. So the first is noise variability. So on this picture here, we show the layout of qubits in the 16-qubit system that we work with. So the circles here are the qubits, and the edges denote the permitted 2-qubit operations in the system. So you can see that each of these links are color-coded depending on the quality of the operation there. So the link between 0, 1, for example, has an error rate of about 10% for the control NOT gate, while the link here has an error rate of about 1%. So if while compiling a program, the compiler was not aware of these hardware variations, it could accidentally place the program or the program qubits here, and that execution would incur a bad success rate or a bad fidelity. And these kind of variations occur, both across qubits in the device and across time, and they also occur in trapped ion devices. So, for example, here we have the qubits in IonQ's 11-qubit system, and you can see that there is a distribution of 2-qubit error rates that are observed across the different pairs of qubits that you can operate in. So, across vendors, across qubit technologies, there is up to 10x variation in the operational qualities, depending on which specific technology we're using. And these kind of variations occur because of fundamental challenges in controlling the qubit states, because of manufacturing defects in the case of superconducting qubits, and to some extent because of external interference. So we expect nearly all devices in the next 5 to 10 years to have these kind of noise variations. And although there have been a lot of prior works on compilation for these kind of devices, these works ignore these kind of noise variations. Many of these works consider the system as a static entity where all the links have the same error rate. And by doing this, there are severe fidelity losses that occur when the executables are not optimized with the noise rates. So because the noise rates change every day and across qubits, there is a lot of opportunity to optimize programs based on the current error rates that we know for hardware. And in the case of devices like IBM's, where the noise variations are very high, for example, up to 10x, it's quite intuitive that these kind of variations will make a lot of difference to programs. But we found that in certain platforms like trapped ions, the variations are more static, so there are less variations across time, and the degree to which noise varies is also lesser. But even in these kind of platforms, we were able to show that the compiler needs to be aware of the noise variations, and the noise optimizations make a significant difference. The next challenge that we have in the software layer is that the hardware that we need to operate on and work with is really diverse. So the hardware is diverse in terms of connectivity. So you can see 3 different qubit wiring topologies. So So devices can have different connectivity topologies. Devices also have different instruction sets and different choices that they make for both the instruction set that they expose to software and for the native gates that they implement. So because of these diverse topologies, there could even be dynamic changes in topology based on the qubit and gate operational parameters. It's important for the compiler layer to consider these kind of topology differences along with the noise information to really optimize programs. So to summarize, from the application side, we want executions with high success rates. From the hardware side, the challenges are high gate error rates, the high variability in the noise, and the diversity in gate sets and connectivity. And at the software layer, the way we want to design this is to look at how can we bring in software techniques that can improve application success rates using device calibration data. And we want to optimize these success rates portably across different vendors and different devices. So the main idea behind our work is to adapt our programs to use the most reliable regions of the device based on device calibration data. So as an example of this, if you have a 4-qubit program like this, where time goes left to right, the qubits are these horizontal lines, and these are the operations happening on the qubits. We want to take a program like this and map it down for execution onto a particular region of the device. So if the compiler was not aware of noise, we could accidentally map it to a location like this, where let's say a C0 gate here has a high error rate. And what that means is that this overall execution would have a low chance of succeeding. Whereas in our work, we can use information about the different links, the information about the qubit coherence times, and find a good mapping where all the links are mapped, all the operations in the program are mapped to hardware links which are good, to hardware qubits which are good, and so on. And one of the key ideas here was that unlike classical computing, where we can compile our program once and execute it many times and get similar performance, for quantum computing, we really need to compile our programs once per execution and use the latest error rates to do that to get high success rates. So there were 3 main strategies that we used to get noise adaptivity. The first was to map program qubits onto the best hardware qubits. The second was to schedule gates to finish before the coherence times of each qubits. So for the more computer science people in the audience, what coherence time means is that every qubit has, you can think of it as every qubit having a limited amount of compute time before which all operations have to finish. And we basically want to schedule our operations to finish before this time, and that influences how we perform the mapping because we want to select qubits which have high coherence times. And the third strategy was to reduce the chances of communication errors. So near-term quantum hardware, especially superconducting qubit hardware, has restrictions in terms of how qubits are connected to each other. So if we wanted to do a 2-qubit operations, a 2-qubit operation between these 2 qubits, the hardware does not natively allow it. And what we need to do is to exchange the state of the first qubit, move it close to the second qubit, and then perform the operation. So each of these swaps or exchanges is very expensive in the hardware in terms of its penalty on the error. And we want to reduce chances of communication and use exchange or swap paths that use good links in the hardware. Now, I mentioned that we want to do this portably across different devices. So one of the main questions here was, how do we handle these different systems with very different connectivities and noise rates? And one of the abstractions that we came up with to make this happen in the compiler layer was to get an abstract representation for the noise and the connectivity information, which is what mattered the most for the compiled executables. So given a device like this annotated by the error rates, we wanted to convert this to a matrix representation where the entry at qubit ij represents what is the reliability or fidelity of performing a 2-qubit operation between qubit I and qubit j. So we can initially fill this out with the calibration information that we get from hardware, and then do an all pairs reliability estimation to estimate the reliability between every pair of qubits in this device. And this lets us take any device with any topology and any set of noise rates and get a common representation that we can use in the compiler. And by expressing all our compiler passes using this representation and working with this representation, we get portability across different devices and different noise profiles. So to actually implement the three strategies that I talked about, we used a formal optimization strategy. Quantum programs that we can run in the near term are still sufficiently small that we can perform formal optimization and try to get optimally compiled executables. So our optimization uses this paradigm called SMT optimization, which is very popular in the classical computing world. And the optimization has three sets of variables corresponding to the qubit mapping choices that we want to make, the swapping or routing choices that we want to make, and the gate scheduling options. And based on these, we have a set of noise-dependent constraints, where for every operation in the program, we have a variable that says, what is the reliability or fidelity of this operation if we chose a particular mapping or a particular swap path and so on. And we also have a set of constraints that say, how much is the coherence time bound on each qubit, and we want the optimization to enforce that. Finally, the overall objective of the optimization is to maximize the fidelity. In practice, the fidelity is something that you measure when you go and execute your program on the real hardware, and it's difficult to approximate or measure that at compile time. So the objective function that we use is a product of the reliabilities of all the operations in the compiled executable, and we determine this based on the calibration data that we have. And there are several works showing that this kind of an objective function closely matches the observed fidelities in practice, and people have shown this both for superconducting systems and trap-blind systems. So all of the ideas that I talked about, we embodied this in a tool flow called TriQ. It's called TriQ because it takes three kinds of device inputs. It takes noise data, it takes information about the qubit topology, and it takes information about the instruction sets and the gate transformations needed to implement that instruction set. And it takes a high-level language program written in the scaffold language, converts that program to LLVM IR, and then performs the steps that we discussed. That is, it computes the reliability matrix, and it constructs the optimization and solves the optimization using the Z3 SMT solver. And as a result of the optimization, we get a set of mapping, routing, and scheduling choices. And there is a set of backend post-processing routines which process that optimization output and generate code that we can directly run on IBM, on Rigetti, and University of Maryland's trap-blind devices. So here we show some evaluation for TriQ, comparing it to IBM's Qiskit compiler. So here we are looking at real system runs on IBM's 16-qubit hardware using a set of 12 benchmarks. These benchmarks have 2 to 8 qubits, and these were the kind of benchmarks that we could run on these systems 2 years ago. And for each of these benchmarks, we run 8,000 shots on the hardware and measure the success rate. And we're comparing TriQ versus Qiskit. So you can see that across benchmarks, our compiler, which uses noise-adaptivity, gets much higher success rates than Qiskit. And the reason was that Qiskit at the time used a lexicographic qubit mapping and a randomized swapping strategy that was not aware of the noise properties. And on average, we get about 3x improvements over Qiskit. In the best cases, we get up to 18x. And even on a communication optimized baseline, we saw that we can get up to 9x improvements because of noise optimizations. And we also see that we get higher improvements for programs which have more qubits. Now, we also performed further experiments to look at the importance of noise optimizations across different platforms. So using 3 systems from IBM, 2 systems from Rigetti, and a trap-blind device from Maryland, we were able to show that compared to the vendor compilers, say Qiskit or Rigetti's Quill compiler, we can get significant improvements in the success rate if we use the noise optimizations and let the compiler look at the hardware noise variations. And I want to point to the UMD results in particular, because when we started doing these kind of optimizations for this platform, there was actually a lot of skepticism from the physics side and from the device engineers, because this system actually had much lesser variations compared to the superconducting systems. So it is not clear whether factors like noise optimization even matter. But using real system runs, we were able to show that even on this low noise system, noise adaptivity can be quite significant. And these kind of results had a significant impact on how industry views compilation. So we released TriQ and other compiler passes that we developed as open source packages through GitHub, and also contributed them to Qiskit. So we contributed the noise adaptive mapping techniques to Qiskit. I don't have time to talk about crosstalk mitigation, but that's another pass that we contributed. And as a result of these contributions and the evaluation across different systems, multiple compilers today use these kind of optimizations. So Oak Ridge National Labs, ZAC and QCore compilers pulled in our optimizations. Rigetti's Quilcy compiler uses noise adaptivity. Cambridge Quantum Computing's Ticket compiler also uses noise adaptive mapping techniques. And recently, IBM also started porting noise adaptivity to other passes that they had. So this work essentially shows the value of software knowing fine-grained hardware noise characteristics in quantum systems, and also the potential for software to really address some of the problematic noise issues in NISQ hardware. So I'm going to switch gears a little bit here and talk about architecture. And I'll talk about how we can use some of the compiler techniques that we developed to understand how architecture should be built. So I mentioned that we have systems which have very restricted fidelities. For example, in most of the current systems, we have 2-qubit gates with somewhere around 95 to 99% fidelity. And what this means is that we can only run programs with a limited number of instructions before noise overwhelms the execution. So one way to get over this is to reduce the gate error rates. And this is quite challenging in practice, especially as systems scale up. So the best systems that we have today have error rates that are close to 0.5%, but it's really hard to push that and improve the depth of the programs that we can run. Another option that we have is to reduce the number of instructions in the program itself. And the main question that we asked here is, can we look at reducing the number of instructions in the program, not from a compilation perspective, but from changing the instruction set itself? So can we redesign a new instruction set which can give us much better program instruction counts? And to give you a sense for how important this is, I'll show you the instruction counts for two applications. So here we have a quantum volume unitary, and we're compiling this using a numerical technique that I'll talk about in a few slides to use two different kinds of hardware 2-qubit gates. So if the hardware had a controlled Z gate, compiling this unitary to use the controlled Z gate would require 3 applications of the controlled Z gate. While if the hardware had a square root ISWAP gate, we would need only 2 applications of that gate. Instead, if we were working with a QAOA unitary, then when we compile this to the CZ gate, we would require only 2 CZ gates. While if we had a square root ISWAP hardware gate, we would need 3 applications of the gate. Now, when we look at a single unitary for QAOA or for quantum volume, it looks like a difference between using 2 gates versus 3 gates. But if you had a series of these unitaries, it's like a difference of 50% between these 2 compiled executables, and that can be quite significant for the full application. So if you look at how prior work looks at instruction set design, there are basically 2 sets of instruction sets that were proposed. So one is instruction sets which had a single type of 2-qubit gate. For example, IBM devices have a controlled NOT gate as the 2-qubit instruction. Early Rigetti and Google systems had controlled Z gates. And the other camp is where there are instruction sets which have continuous 2-qubit gates. So for example, this XY family of gates here has a parameter theta that you can control to get different kinds of unitaries from the hardware. And these kind of continuous instruction sets have been proposed by different vendors now as a means to reduce program instruction counts. So what are the trade-offs for applications and for hardware here? So when the instruction set has a single type of 2-qubit gate, This is very easy in hardware to calibrate because you just need to tune up the operational parameters for one type of gate. But it becomes too restrictive for applications, as we looked at earlier. And for certain applications, it can potentially increase in instruction counts by quite a bit. And if you look at the continuous instruction sets, then these kind of instruction sets are very good for expressing applications and getting very low instruction counts in the program. But they're extremely challenging to calibrate in practice because there's literally an infinite number of gates that we need to tune up. So in practice, what vendors do is to select a set of angles. So impose a grid on the continuous space and tune up a large number of angles in that space and use interpolation techniques to get gate implementations for all the angles. And this can consume a significant amount of calibration time, as much as several hours or almost the entire operational time of the system can be used for calibration. And these trade-offs between how the instruction set behaves for applications and for hardware are quite similar to the RISC versus CISC trade-offs that were dominant in classical architecture. And the main questions that our work asks here is, can we design an instruction set that is both highly expressive for applications and also very easy to calibrate? And to reduce the calibration overhead, we really wanted to use very small subsets of instruction sets. So in particular, we were asking whether can we take a small subset of this continuous instruction set and look at what are the application trade-offs for that. And the way we studied this is by using some of the compiler tools that we had built. So this is our overall framework for studying the instruction sets. Here, we wanted to look at a set of near-term quantum applications. So we looked at quantum volume, QAOA, Fermi-Hubbard, and QFT. And we wanted to study different instruction choices. So the toolflow supports a configurable instruction set to test continuous instruction sets, to test a discrete subset of those, and test a single 2-qubit gate in the instruction. And we developed a compiler pass that can basically take a set of application unitaries, a set of an input instruction set, and generate a compiled executable where the application unitaries are expressed in the most efficient way possible using the hardware 2-qubit gate types that we have. And as some validation, we compared with Google Circ compiler and showed that we can get 1.3 to 2x lesser instructions than executables that are compiled with Circ. And as the output of this compiler, we get a compiled executable that we can go and simulate with a noise simulator and determine metrics like the number of instructions in the program, the fidelity of the output, and so on. And to study the calibration trade-offs, we built a calibration model based on Google's 54-qubit system that was used for the quantum supremacy experiments. So the main finding from this work was that we really should be using instruction sets which have 4 to 8 types of 2-qubit gates. The way we did experiments to determine this was take application unitaries. For example, here we show quantum volume unitaries, and we compiled that to use the entire spectrum of gates available in the continuous gate set. So here we are looking at the spectrum of gates available with Google's FSIM gate set. So there are 2 angles in this gate set that we can tune, the theta and the phi angles. And this heat map here shows what is the average number of instructions required for expressing a single application unitary using a particular a parameter combination of this gate set. So spots that are lighter in color are better because the instruction counts there are lesser. And by performing these kind of sweep studies across applications, across the gate space, and running noise simulations, we found that when we use 4 to 8 types of 2-qubit gates, that's actually sufficient to get significant reductions in the instruction counts and improvements in the fidelity compared to just using a single type. But it's also very close to using the entire gate set. So what that means is that we don't really need to calibrate the entire continuous set of 2-qubit gates. We just need to pick the right set of 4 to 8 types and calibrate that. So that basically gives us a very large reduction in the calibration overhead and it lets us get the best of both worlds. That is, we can get an instruction set that is very, very good for applications, but also very easy to implement on the hardware. So that was our recent work on designing instruction sets. If you want to know more about this, you can check out our paper at ISCA 2021 coming up in June. And now I'll briefly talk about two avenues for future work and conclude. So to lay out our future work, I want to first discuss some of the impact that we have had on real compilers and industry instruction sets. So here I show the timeline of the work that we've done in the compilation space. So we looked at optimizations like noise-adaptivity in 2019, and as part of extending that work to other systems, we looked at how we can portably compile for these devices across superconducting and trapped ion systems. This work had a lot of impact on industry, as I mentioned. Multiple compilers today use these optimizations. Subsequent to that, we looked at this hardware problem called Crosstalk, where we looked at the first software strategies for reducing crosstalk error in hardware. And this set of optimizations is now used in IBM, and it has influenced how other vendors think of crosstalk benchmarking, and also influenced IBM's new OpenChasm standard. And they introduced new operations to support these kind of optimizations. And as a result of our ISCA 2019 work, which looked at portable compilation, in addition to just being a portable compiler, it helped us understand cross-platform architectural characteristics. And in particular, it helped us understand insights like exposing native gates to software to let compilers have visibility into hardware and perform more extensive optimizations. And these insights were used by IBM for one of their recent quantum volume demonstrations. And as a result of this, IBM also started exposing more native operations to software in their recent devices. And subsequent to this work, we used insights on designing native operations and connectivity to look at design for trapped ion systems and for the instruction set design work that I talked about. So as we look at the hardware and the application space that is evolving in quantum, we have new devices with new capabilities like mid-circuit measurements, feedback control, and upcoming technologies like photonic qubits and neutral atom qubits. And we also have at the top of the stack hybrid applications that are very promising in quantum chemistry, optimization, and other fields. So to support these kind of applications, our work shows that it's going to be very important to have a cross-cutting approach and a cross-cutting full stack approach for designing the intermediate layers in the quantum stack to really make the best use of emerging hardware and enable the best executions for applications. And as we look forward into the 5 to 10 year time frame, we are likely to have the early or the first devices which are capable of some form of error correction, and in the larger future, systems with 50 to 1,000 qubits. And to really enable application executions on these systems, my work shows that it's not enough to just build a hardware from the bottom up and then decide what we're going to have in the instruction set layer or what we have in the compiler layer. But we really need to go both ways. That is, we need to design architecture based on the requirements of these important application domains, based on the requirements of the error correction techniques that we want to use, and have design that is going both up and down in the stack. So we envisioned that techniques like domain-specific accelerators that have been very useful in classical computing will also likely be very important for really enabling near-term quantum applications. So to conclude, there is a large gap that we need to address to really make quantum computing happen in practice. To bridge this gap between the algorithms and devices, our work shows that computer systems research, architecture, and compiler techniques have a very crucial role to play. And cross-cutting optimizations like noise-adaptivity and co-designing the hardware and software have the potential to offer anywhere from 2 to 4 orders of magnitude improvements in the fidelity. And with the kind of error rates that we have in near-term devices, these kind of improvements can make the difference between failed application executions and successful executions. And it's also important, and these kind of optimizations are also very important to make the best use of devices that we have now, and also to enable progress towards larger fault-tolerant systems. These works have had a lot of real-world impact, and in the future, there is scope for further narrowing this gap through cross-cutting stacks for emerging hardware and domain-specific architectures. If you want more information about our publications, here are some links, and we're happy to take questions now.
Well, thank you so much, both Margaret and Prakash, for the great presentation. We received a few questions during the presentation. Let me just read the top one. It was about, in Margaret's part, she mentioned the existence of several industrial compilers, and the question was which ones she were referring to. Would you like to field that question, Prakash or Margaret?
Yeah, I can take that. The compilers that we were referring to were IBM's compiler, Rigetti's compiler, the one from Oak Ridge National Lab, and from Cambridge Quantum Computing. So these compilers pulled in noise-adaptivity and other optimizations in some form or the other.
Great, thank you. Then there was a question I had actually in the part where you described the two challenges, the general challenges of noise variability and connectivity. I just wonder, like, to what extent these challenges make the design of libraries that are reusable and scalable. Like, what are the implications for designing such libraries?
By libraries, do you mean libraries which have application routines in them?
Yeah, good question. Like, I have in mind like libraries, say, for arithmetic or for special purpose transformations that are occurring often in quantum computing. Let's say the Fourier transform or so. Like, what are the, as you have this moving target, right? That could depend on a particular calibration run, a particular cooldown. Like, what are the challenges when it comes to designing libraries that are then hopefully reusable?
Yeah. I think one of the goals that as compiler designers that we want to ensure is that applications can still be somewhat independent of the hardware. So by having portable optimizations work well across systems, what we're really giving is, the ability for application designers to be still quite agnostic about the kind of circuits that they're building. And to some extent, or to a large extent, compilers can give significant noise and connectivity optimizations. But we have shown that both on the hardware side, the hardware needs to be aware of the application characteristics to really get high fidelity. And I feel like it's true in the other direction too, that if you really want very high fidelity executions, then it's not enough to just take hardware agnostic application components and try to compile them in the best way, but there's scope to even redesign that part and try to have the application instruction mix and the application instruction patterns be somewhat tied to the hardware. I mean, that may be useful that should be useful in certain instances, but for generic cases like what you mentioned, I think having the portability in the compiler and the optimization capabilities is very important.
That makes a lot of sense. Yeah. A question related to this perhaps is a question about fidelity of the gates that could be obtained, say, by measuring out the system first in calibration runs. So the question was about how does the definition of reliability relate to bounds on the fidelities that might be known? And there's recent work, for instance, by Kimmel et al. That give like limits on the fidelity that you can achieve by certain methods, say randomized benchmarking of the system, and the ways to estimate the unital, non-unital parts of the channel using that. So how do you take into account this kind of fidelity information in your compilation flow?
I'll start this and then Prakash can add to it maybe. I think the jury is still out on the best ways to get benchmarking data that then can drive different compiler optimizations. And so what was done here was based on this sort of abstraction about connectivity and error rates in one. And the nice thing about that is it's simple. It was based on data we could actually get, and it was portable across many different designs. And those are great attributes. I think we would like to keep those kinds of attributes going forward. It's possible, you know, there's an awful lot of attention again now on notions of benchmarking and sort of proxy tests, proxy programs that can go up and down the stack. And so it's possible that we will come up with other ways to express fidelity that are actually even more helpful in doing this. But for now, I think the simple approach has shown itself to be quite portable, which is a good attribute.
That's great. Thank you, Margaret. So we have another question regarding the tool chain. Where do you see the benefits of using LLVM specifically in designing a tool chain? Maybe again, Margaret, if you could share your thoughts, and Prakash then.
Oh, well, I can start. LLVM is widely used on the classical side of the world, and so it has that familiarity, at least from that side of the world. I don't, and it also sort of gave, in the early days, it gave us a leg up in terms of getting sort of parsers and so forth. In terms of how to actually build compilers for quantum, I'm not particularly tied to LLVM. I think it has at times been sort of challenging to plug into. And I think Prakash, who's worked more recently and isn't always using LLVM, can speak to a little bit of that.
That's true. And I think one aspect where we have seen this is that although we built our optimizations using LLVM, all the compilers that picked up these optimizations, I don't think they are based on LLVM. For example, Qiskit uses its own DAG representation and it's entirely written in Python. For the other vendors, for example, I think it's the same with Rigetti as well. They have their own custom representations for quantum programs using their Quill ISA, and they were not really tied. Like the optimizations that we built were not tied to the LLVM infrastructure itself. That was just one way of demonstrating that, and something that we used because we had a lot of LLVM compiler infrastructure at the time. That's great.
And to put in a shameless plug, like in the QIR, which is a Microsoft-led effort, but also community-focused effort for an IR, we're seeing that even the classical passes, like the LLVM optimization passes that are already there for classical code, give us a lot of savings in the produced IR. That's great. So I have another question regarding the crosstalk mitigation part that you mentioned, and you didn't really have time to talk much about it, but you mentioned that it's already picked up by the QCore framework developed by Oak Ridge and by Qiskit. Can you say a little bit more what techniques you apply for crosstalk mitigation?
Sure, yeah. So crosstalk is basically, to set the context, crosstalk occurs when we want to run parallel operations. So if I have, let's say, a 4-qubit system and I run a 2-qubit gate in the first 2 qubits and a 2-qubit gate in the next 2 qubits, and I do this in parallel, then the error rates for both of these operations worsen, and they worsen by significant amounts. So prior to our work, all of the work on mitigating crosstalk was changing the hardware connectivity. So IBM moved from grid-like devices to larger hexagonal rings, and this was in part because of heavy crosstalk in the grid devices. So there were approaches looking at hardware redesign, changing how instructions are implemented, and so on. But what our work showed is that if you actually look at the capabilities of software, and we try to think of crosstalk as a software level problem, then we can actually do very well in terms of mitigating that using compiler techniques. So one way to mitigate crosstalk is to serialize the instructions so you don't have parallelism. And you can do that and get rid of crosstalk, but that basically increases the chance of decoherence errors because now your program runs for a really long duration. So you want an execution where you want to minimize crosstalk, but you also want to minimize decoherence, and those are conflicting objectives. So at the compiler layer, what we did is to use crosstalk characterization information from the hardware and decoherence data that we have from regular vendor calibration, and sort of take a a global optimization view of the program and see, what is the best way to serialize or parallelize instructions in this program that I get the best overall fidelity, which mitigates crosstalk and mitigates decoherence errors. So similar to how we used SMT optimizations to do the noise adaptivity, we found that the same or similar kind of techniques, the similar kind of optimization techniques work for crosstalk mitigation as well. And that's the full details of this are described in our ASPLOS 20 paper. Okay.
Sounds like a hard optimization problem in general, right? To figure out the best mapping. What optimization techniques do you use?
We were specifically looking at only scheduling the operations. We were not really looking to change mappings based on crosstalk. So this was supposed to be, the compiler first decides a reasonable mapping, and then it tries to deal with crosstalk only in the scheduling step. So for every instruction, we want to determine what is a good time to start this instruction with respect to the other instructions.
Perfect. Well, thank you very much. Thanks to our presenters for sharing such an inspiring talk and very hot off the press results that some of them will be presented at ISCA, I believe, this summer, right?
Yes.
This is exciting. Thanks a lot for the great questions. And I think we're at the end now of this seminar this week. Yeah. See you all. Thank you.
Thank you.
Thank you.
Thank you.
Goodbye.
Bye.